part 2 of our VSEPR podcast, and this one we're really going to look at the bond angles and what these things look like. So if we start at the very top, yesterday I kind of had a drawing. It's this first one right here, this B, A, B2, I guess. And what we're going to be building in class is stuff that looks like this. I happen to have a yellow, let's pretend this is A, and our two reds are B's. And they're connected with double bonds. So there's two little kind of bendy plastic things that are holding them together. And essentially what happens is, if we have two areas of electrons, and if we're thinking in three-dimensional space, they're going to repel each other as far apart as possible. So if there's two things, they're going to be 180 degrees from each other. So from this red to this red, there would be a 180 degree angle. So our bond angle is simply 180 degrees. And then what this drawing might look like, because I can put this in a plane of a paper, there's not much three-dimensionality to it. So we might just have A, B, B. And we don't need to have three-dimensional because it's in two dimensions. All right. Our next one, if we kind of look at it, we have two shared areas. And actually, I'm going to skip to this third one. I think the Trigonal Planar first. It's going to look something kind of like this. So it's fairly obvious that it's a triangle. All right. So we have A with three B's around it this time, and we have a double bond at our top B, and then we have single bonds down here at the bottom. But there's three areas of electrons, and there's no lone pairs. So again, if we kind of come over here, three areas, zero lone pairs. So if there's three things repelling each other, they're going to want to get, again, as far away as possible. So they're going to repel each other 120 degrees. And again, if we look at this from the side, so it kind of looks like a triangle this way. But if we look at it from the side, we notice that all these atoms are in the same plane. So we could put a piece of paper, and they'd all be in that same plane. That's why it's called Trigonal Planar. And as far as three-dimensional looks, it doesn't have to be three-dimensional, but it might just look like this, with kind of just lines bonding to each of our B's at about 120 degrees apart from each other. Okay? So again, we can have three like this, or we could have two bonding and one lone, and that's going to look something kind of like this. So notice, I still have three areas. I have an area above my central atom, I have one to the left, one to the right. They happen to be single and double bonded. But this area of electrons, even though it's not bonded to anybody, it still repels these two bonds. All right? So my shape, notice it's bent. So my shape only refers to my molecules, or my atoms in my molecule. So if I kind of take this off, what do I have left? I have a bent shape. It's not linear anymore. It is bent. If you want to leave this on or leave it off, it doesn't matter to me. I think it makes a little bit better sense if you're building these in class to leave this here. And this without a ball at the end just represents a pair of electrons. So this one we're just going to call it 120 degrees as well. You're fine memorizing that. In all actuality, this lone pair pushes these a little bit closer, so it's actually a little bit less than 120 degrees. Let's see. And this, again, we don't need three-dimensionals really for it. We might just have something kind of like this, and then we're going to have a lone pair at the top. All right? So is that less than, greater than 120? I'm going to put this over here. So less than 120 degrees. But for my purposes, 120 is fine. But no, in actuality, if you go on in chemistry, it's really less than 120. Our next one, 4 shared, 0 lone, is going to look something like this. And what in the world does tetrahedral mean? Well, if you remember back when we named compounds, tetra means 4, or if you think of the game Tetris. So if, it's kind of like a pyramid more than a tetrahedral, but this has 1 side, 2 side, 3 side, 4 side. So it's a 4-sided shape, which is why it's called a tetrahedral. Again, if we kind of just connect the outer dots and make planes between them. So it's called tetrahedral. And now we have 3 dimensions. There's no way I can put this I can look in it any direction to have them all on the same plane. So our bond angle is not 90, but it's actually 109.5. All right. And the way we might draw this is I can kind of put it like this, so that these two whites and this black are in the same plane. And then we have an electron going, or an atom going towards you, and one going away from you. So the way we might represent this might look something like this, where we have A attached to a B up here and a B over here, and then we kind of draw like a little triangle, and color it in, and that's supposed to be a B coming out of the board, and then kind of a little dash is a B going into the board. And that's how we might represent it three-dimensionally. All right. Our next one is if we just remove one of those. So now I have 3 bonding and 1 lone again. So again, this lone is still repelling everybody, but now we don't really think of it in terms of our shape. So again, we have a triangle, but now it's not in the same plane. Notice it kind of looks like a pyramid. So that's the name trigonal pyramidal, because this lone pair is repelling, they can't be flat, it's repelling them away. So this is, again from my class, no 109.5, but no, in all actuality, it's less than 109.5. How come? Because the lone pair repels more strongly than the bonding pairs. Alright, it kind of takes up more space up here and forces them down. The way this might look in 3 dimensions would be something pretty similar to the last one. We might have A going up to B, going out to B, coming out of the board to B. Ooh. And then we might just have kind of our electron pairs over here behind the board. Okay? Our last one, if we just take another one of these off, it might look something like this. So we still have 4 areas of electrons, but 2 are bonding and 2 are lone pairs. Okay? So again, if we kind of ignore the lone pairs with our shape, we have a bent molecule again. Looks just the same, except this bent molecule is not 120 degrees, but it's 109.5 again. So notice the bond angles always match your areas of electrons. If it's 4, it's always 109.5. If it's 3, it's always 120. If it's 1, it's always 180. Again, this can be less than 109.5 again. And then the way we might draw this would just be pretty similar to, again, our last 2, where we just have A up to B, out to B, and then we kind of have electron pair out here, and electron pair into the board. Okay? So we have 2 bents. Know that. There's two ways we can get a bent shape. Otherwise, our shape looks like the shape that our actual atoms make. So you kind of might pull the electron pair off, but know it is there, and it's repelling electrons, even if it's a lone pair. So that is it for day 2, or part 2, of valence shell electron pair repulsion.